Lab 5, Choose Your Own Adventure, Falling Slinky Lab, and this is for Physics 2211. So for the introduction, the purpose of the lab is to show our understanding of physics principles by choosing our own physics video and applying principles and teachings we've learned throughout the year. Discover if the bottom of the slinky remains motionless after it drops, and to compare and contrast the observed and predicted models. So for the experiment, we observe and analyze the motion of a falling slinky drop from equilibrium using tracker to analyze the falling motion and create graphs, and coding via glow script to create a computational model based off the physics principles. So the physics principles that are used are Newton's second law, which we use to find the velocity update formula and the position update formula. And also the gravitational force, which is negative mg in the y direction, the tension force of the slinky on itself, which is the force of gravity is equal to the force of tension, and the drag force, which is equal to b times the magnitude of v squared times j hat. So the net force is also equal to mass times acceleration, which is mass times the change in velocity over the change in time. So here's a preview of the results. As you see over here, we have the graph of the slinky's motion plotted on a y versus time graph. And yeah. So here's the video we have. And you can see the slinky falling and as it hits the ground. So I put this video into Tracker and tracked the motion as shown in the slide beforehand. So the initial conditions of the code, so the height is the man in the light blue shirt as the calibration stick, and then I tracked the slinky's motion from the bottom of the slinky as the point of mass, and the mass of the slinky was 0.218 grams, and the origin of the plane to be the bottom of the slinky. The slinky is a system, and the surroundings is the Earth. So here's the code. As you see, I put the mass, the slinky in there, and then have the position and the velocity as 0, 0. And then you set up the time, and then the constants we found b, which is the drag constant from trial and error. And then so while the time is less than 1.25 seconds, the force of gravity on the slinky we set to be the negative g times the mass of the slinky in the y direction, and then the force of the tension is the positive of that, and then the net force is equal to the force of gravity plus the force of the tension. So using the momentum principle, we put in the velocity and position update formulas and then change the time. Down here we have what created our plots for our predicted model. So then we also have, while the time is less than 1.81, which is the time the slinky dropped, we still have the force of gravity and the force of drag we add in because as it's falling, of course, the drag force is acting on it. And the net force is the force of gravity plus the force of drag. And we also put in the velocity and position updates again, and then set up the graphs and change the time. So here are two different models. Over here with the green line, we have the model from the computational model from the GlowScript code, which as you see, the net force is going to be 0 up until the slinky is dropped. And that's also pretty much the same as our tracker one, just with the differences in where I chose the bottom of the slinky, which is an error on my own fault. But then they both go down after the slinky is dropped, and the net force is not equal to 0 at that point. So what does it mean? So the net force is constant until the bottom and the top of the slinky meet, because the tension force of the slinky being stretched is equal to the force of gravity at that moment. And until then, the slinky bottom remains motionless, and this is due to the tension upper part of the slinky and the force of gravity, creating a net force equal to 0, as shown in the graphs of the horizontal move horizontal plot until it hits. So once the tension is released on the bottom of the top meat, then the whole slinky starts to fall, and the net force is the force of gravity minus the force minus the force of drag. So we can see that in the differences of the models and the error that could have occurred. It could have been my my human error of just plotting the position wrong on the on tracker, and even like calibration and everything could be off. But yes.